let's say this is the vector function that is given to us, and we want to find line integral for this vector function along a line. And let's say this is the line that we are given with. So we have x, y, z coordinate system. So this is my x axis, this is y axis, and this is z axis. Okay, and let's say here is a point with coordinates 1, 1, 1. Okay, since it has 3 coordinates x, y, z, this means that this point is in space, it's not in any plane. How can you show that on this diagram so that it makes sense that it's in space? So you can draw its projection onto the xy plane, and then you can make it look like, you know, a 3-dimensional point. And then this line starts from region. So region has coordinates 0, 0, 0, which means the x, y, and z has 0 values at this point. So let's say we want to calculate line integral of this vector function along 3 different routes, and we can choose different routes. Let's say the first route goes along this green line. So it starts at origin, goes to 1, 0, 0. So this point has coordinates 1, 0, 0, which means we have traveled 1 unit along x-axis but no distance along y or z axis. So this point has coordinates 1, 1, 0. So now we are 1 unit away from x-axis, 1 unit away from y-axis, but still no distance along z-axis. We want to get to this point. So the third path will be this one. So first we calculate the line integral along this green path. We can also take another path. Let's say we instead go first along the y-axis along this red line, and this point has coordinates 0, 1, 0. Then we go along this red line, and this point has coordinates 1, 1, 1, 1, 1, 0. We have already written them. And then finally we go along this line and get to point 1, 1, 1. And finally we have another option too. We can go directly along this blue line from 0, 0, 0 to 1, 1, 1. Now we know that the line integrals tells us as long as our starting point and our end points are same, no matter which path we take, we should have the same answer. That's what the line integral is. So basically we want to calculate this quantity. We want to calculate v dot dl. We want to calculate this quantity along these 3 different routes, and dl is the length element. It's given as dx, x unit vector, plus dy, y unit vector, plus dz, z unit vector. That's the length element for x in space along x, y, and z directions. So 3 colors, green, red, and blue, and 3 different paths, all starting at 0, 0, 0, ending up at 1, 1, 1. I'm going to solve for 2 of them. Let's solve for green path and then this blue path. The third one I'll leave it to you. Okay. So we want to calculate this quantity v dot dl, and this is the vector field or vector function v. Okay. So when we travel, so what we do, we want to calculate the total line integral along this green path. Okay. So you can divide this path into further 3 parts. Let's call them 1, 2, and 3, which means that we have to calculate line integral along these 3 paths, and then we'll add them to get the total line integral. So when we move along this first path, which takes us from coordinates 0, 0, 0 to 1, 0, 0, in this case, so this is the first case, x goes from 0 to 1, x changes. But y and z, we have not traveled any distance along them, and so they are 0. Okay. From here, we immediately infer that dy should be 0 and dz should be 0. Okay. This helps us simplify our formula a lot. For example, if we use y and z equals 0 in this formula, we are only left with the first term. Okay, because y and z are 0. And if we take dy and dz 0, then in the dl we are only left with this first term. So for the first path, our integral v dot dl, this gives us x squared integral x squared x unit vector dotted with dx x unit vector, and this immediately gives us integral x squared dx. Okay, and now you can, along x-axis we have gone from 0 to 1, so it has limits 0 to 1, and this immediately gives us x cubed by 3, which becomes 1 divided by 3. So this is the line integral along this first line. Then we move from this point 1 0 0 to 1 1 0. This is the second path that I named as 2, and along this path x is 1, so this gives dx equals 0. Y along this path is changing from 0 to 1, and z along this path is 0, and so dz equals 0. And now if we substitute z equals 0, dz equals 0, and dx equals 0, dx, this first term makes this first term 0, dz makes this third term 0, so from dl we only this middle term survives, and from v, if we use if this middle term survives, it means we only need to look at this middle term, because then we are taking the dot product of this y unit vector with y unit vector. Dot product of y unit vector with z unit vector or x unit vector will automatically be 0. Got it? So we are only left with this middle term, which gives us integral v dotted with dl equals integral 2 yz y unit vector dotted with dy y unit vector, but then z is 0, and so this gives us 0. So line integral along this green line is 0. Now we have this third green line, and for this third green line, third path, x is 1 and y is 1, but dx, this gives us dx equals dy equals 0, but z in this case, it goes from 0 to 1. Okay, so line integral will be v dot dl equals, let's first look at v and let's first look at dl. So dx is 0, dy is 0, so dx is 0, dy is 0, so only third term survives. Okay, and then we have z unit vector. It means that we take only the term with z unit vector from v, and this has y square, and y square is y is 1. So v dot dl, this, if I write it explicitly, this becomes y square dz, y square z unit vector dotted with dz z unit vector, and this gives us integral, this dot product gives us 1, y along this path is 1, so this only becomes z, it just becomes dz. Okay, and integration limits are from 0 to 1, and this gives us 1. Okay, now we had divided our original path, this path, into 3 segments, and we have calculated the work along all those 3 segments. and the work has turned out to be 1 by 3, 0 and 1. So the total work along first path, total line integral, it is actually related to work, but total line integral along these three parts is 1 divided by 3 plus 0 plus 1, which gives us 4 by 3. So along this green path, the line integral gives us 4 by 3. At the start of this problem, I claimed that no matter which path you take, your answer should match. So I will leave this red path for you, but I'm gonna solve this blue path because this is the most important in this one. Why? Because in along this blue path, we go from 0, 0, 0 directly to 1, 1, 1, which means at the same time when we move, x coordinate changes, y coordinate changes and z coordinate changes. If you look at this situation, one of the coordinates, in fact 2 of the coordinates out of 3 goes to 0 directly, because you see here y and z are 0. In the second case we had dz 0, dx 0, so again 2 terms goes to 0, and the third one again dx and dy are 0 and 2 terms goes to 0. But here no term goes to 0, so we have to actually evaluate it. And for that, in order to carry out the integration, now that we will have x is related to y and y is related to z, because when you move, the distance along all three axes changes. So you have to find a relationship between x, y and z. And I am going to do that. To find that relation, you need to find equation of line through 3 points. Equation of line through 2 points in space. So each point in space is represented by 3 coordinates. So the general formula for finding equation of, I'm going to erase this part. So general formula to find equation of line through 2 points in space is this: x minus x1 divided by x2 minus x1 equals y minus y1 divided by y2 minus y1 equals z minus z1 divided by z2 minus z1. And now you ask yourself the question, what are these things? What are x, y, z, x1, y1, z1, x2, y2 and z2? Okay, so your line, this blue line, it passes through 2 points 0, 0, 0 and 1, 1, 1. So these coordinates, they are called x1, y1, z1, and these coordinates, they are called x2, y2 and z2. So we substitute the values of these coordinates. So this becomes x minus 0 divided by 1 minus 0 equals y minus 0 divided by 1 minus 0 equals z minus 0 divided by 1 minus 0, and this gives you x equals y equals z. This tells us that if you take this route, if you take this blue path directly from origin to this point 1, 1, 1, your x is equal to y is equal to z. Okay, which means that in this vector function, you can write this vector function instead of 3 variables in 1 variable of your choice. Okay, so in this vector function, let's substitute y and z equals x. So this first term is x square x unit vector. If I substitute y and z as x here, so this becomes plus 2x square y unit vector, and this becomes plus x square z unit vector. Okay, right? And now we take the line integral. So now we take v dot dl, line integral, and this becomes integral dot dl. We need to dot this first term with this first term, so this becomes x square dx plus this second term becomes 2x square dx, and third term becomes plus x square dx. Okay. And if we add these terms, they are x square plus 2x square plus x square, so they becomes integral 4x square dx, limit 0 to 1, and this gives you 4 times x cubed divided by 3, limit 0 to 1, and that gives you 4 divided by 3, precisely as we intended. Okay. So I wanted to solve this because this is the part which is not solved in Griffiths. He just assumes that you know how to find equation of line passing through 2 points, which means you know how to find the relationship between 3 coordinates x, y, and z. Okay, but this is important. So this point is important. So if now you try to solve, try to find the line integral along this red path, you should still get the answer 4 by 3. Okay. We good? Good. So let me erase all of this and let's move to the second one, the surface integral. And surface integral is interesting. It's also related to another term which gives us the divergence theorem. So let's take a cube. So this is surface integral. They are very easy. So let's assume we have this cube, this surface lying in our coordinate system. So again, x, y, z. How do we make a cube out of it? Let's say this is the back side of the cube. So this becomes something like this. Not really a good cube, but still a cube. Okay. So this is our cube. It has 6 surfaces because it has 6 sides. So each side is a surface. And we can now name them as the first surface is coming out of the board, the second surface is going into the board, third surface is going to the right, fourth is going to the left, and then we have top and bottom, 6 surfaces. Okay. And we also need a vector field in order to solve it, to see how it is solved. So let's take this vector field. So let's assume that we are given this vector field v equals y square x unit vector plus 2 xy plus z square y unit vector plus 2yz into z unit vector. Okay, this is the vector function that we are given, and we want to find the surface integral. And the surface integral is given as we have surface integral v dot dA. And if you wish, this surface integral can also be written in terms of volume integral. So this is like divergence of v dv. You can also calculate this one. But let's first solve, let's actually prove this divergence theorem. So let's calculate this side first. And you know this operator we call del operator. It's given as x unit vector partial x plus y unit vector partial y plus z unit vector partial z, where partial is given as partial by partial, let's say xi. Okay, I is x, y, z, or 1, 2, 3. It just represents the first, second, and third term. Okay, this is, let's write it like this. Okay, partial by partial x, x, y, z in general. Okay, so if we take, let's calculate this right hand side first. So this will be volume integral. And if we take the divergence of this with this, so the first of this will operate on this term only, and this gives us 0 because we don't have any x function here. So let's calculate divergence of v. So this will gives us, first term gives us 0, second term gives us 2x, and third terms gives us 2y. So this becomes 2 into x plus y. Okay, is this fine? This is just the dot product.
Yeah, and the question was, could you, I'm assuming that the dA is going to have components to it as well, like x hat, y hat, z hat, the differential area product?
No, I'm calculating this side first. So I have just calculated this del dot v. So now I'm going to take its volume integral. So volume integral, I'm actually, it's a surface integral, but if with this right hand side, this is called divergence theorem. Okay. So it's also a proof that divergence theorem holds for any vector function.
Yeah,
okay.
I follow that. I was speaking
No. I'm going to come back to this one because that was a bit lengthy, so I started with the shorter one. Okay, so now we have del dot v dv. This will be 2x plus y, and dv will be dx, dy, dz. That's the volume of the cube. Okay, and now it's easy. You can calculate this integral. This will become equal to 2 integral of x dx, integral of dy, integral of dz plus 2 integral of dx, integral of y, dy, and integral of dz. Just let me know that if this is clear. It was addition, so I had separated it into two terms. And this is a, let's say it's a unit cube, which means its length along x, y, and z axis is 1 unit. It starts from 0 and goes to 1. So our integration limits will be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. And if you carry out this integration, this totally just turns out to be 2. It's just 1 plus 1. Okay, right? So this one was shorter and easier bit. Now we have 6 surfaces when we want to calculate this term. So we want to calculate this term 6 times, 1 for each surface. So this surface, it's directed along x-axis. So its area is dy, dz, x unit vector. Okay. So this becomes, for the first surface, this integral becomes surface integral v dot dA. This becomes v dot. I'm just writing v because it's gonna be simplified. And dA will be x unit vector for first surface dy, dz. And this x unit vector tells us that it's, since it's being dotted with, so only this term survives. Okay, so this becomes, let me write it here. So this becomes surface integral y square dy dz. Okay, and this is just an integral, so you just need to, yes.
So my question was, does the differential area, are there more components than that? As in, like, is there like a y and a z hat component that comes out of the differential operator in that dot product?
Here?
Yeah.
We don't have a differential operator here. It was only on this right hand side.
Oh, I don't like the d.
So dA, this is the area of the surface that you are calculating this function for. So for now, I'm just taking the area element of this surface, which is facing us. For this surface, this lies on the x-axis. So its direction is towards positive x-axis. And so this x unit vector. Okay, and its total area, it's a two-dimensional area which is lying in yz plane. So differential area will be dy dz. Okay. Yeah, it's gonna change for each surface that we consider. So first we are just considering this surface that is coming out. So its direction is towards positive x-axis, and it's lying in the yz plane. Okay, so this is gonna be dy dz. That's what I have written. Okay. Okay, so far so good. And now we can integrate this surface. We have units of area, so this will be y cube divided by 3, 0 up to 1, and then dz, the integral of dz will be z, and this gives us 1 divided by 3. Okay, that's the first surface. Now let's consider the surface which is going into the plane of the page, this back surface. Okay, for this one we get the answer minus 1 by 3. You know why? We will have the same area element, but now it's facing towards negative x-axis. So this term becomes minus of, so for second surface, this term becomes surface v dot dA, this becomes v dotted with minus x unit vector dy dz, and this gives us minus 1 by 3 because it's the same thing but with a minus sign. Okay. Now we have calculated for 2 surfaces, we have 4 more surfaces, so let's try and do let's do this surface. Okay, let's do this surface now. This surface is facing towards y direction, so its area will be, so let's do this third surface. Surface integral will be v dot dA, and this will be v dot dA will be y dx dz. You see why? Yeah, because it's facing towards y-axis, positive y-axis. And this immediately tells us that when we take the dot product of these two terms, only this second term survives because it's y dot y. Y dotted with x and y dotted with z will give us 0. And second term survives, and we write this second term, and this second term gives us integral. Second term is 2 x y plus z square dx dz. Okay. And now if you note that this surface lies at a distance y equals 1 from the origin, this surface. Okay, so we substitute y equals 1 here, and we are left with 0 to 1, 2x dx, and then z square dz, 0 to 1. And this will give us x square by 2, 1 multiplied by z cube by 3, 1 multiplied by 1 by 3, the answer will be 1 by 3. Okay. Will it be 1 by 3? It will be 1 by 3 plus 1, so it will be 4 by 3 actually. So this answer will be 3. We have a plus sign here which I missed. Okay. So going in the same way, you can calculate this for every surface. Let's say now we take this surface which is going towards negative y-axis. Can you see what the answer will be for this surface? For this surface, will it just be the negative of this one? It shouldn't be.
It shouldn't be.
Yeah. Why? Because this surface lies at y equals 1. This lies at y equals 0. And when we use y equals 0 in this term just gives us 0. So integral remains only on the second term, and the contribution from this second term is 1 by 3. So for that surface, the answer will be minus 1 by 3. I don't need to write it, right? Because we are running out of time, and I really want to solve the volume integral because that's the nasty bit. Okay. So now we have this top surface. This lies at z equals 1. Okay. This lies at z equals 1. So in this term, z will be 1, and we have only y integral. So this will be just 1. You see why? You substitute z equals 1, you have integral of dz and integral of dx and 2y. Integral of 2y will be 2y square by 2. 2 cancels out, we get 1 multiplied by 1 from x integral. So this gives us 1. And this gives us z equals 0. So this term goes to 0. And so the term goes to 0. And everything adds up to 4 by 3. Do you see? 1 by 3 minus 1 by 3 is 0. 4 by 3, okay, and 1 by 3. and we are getting 0 from there. They just add up to 2 where we started with. So you get the total answer 2. Okay. And this not only proves the divergence theorem, which is this expression, it also teaches us how to calculate the surface integral. Okay, so there was nothing special about surface integral, just to knowing the steps and how to calculate it for a given surface. For line integral, we had one important thing, that was finding equation of a line passing through 2 points in space. That was the important thing. And we are going to deal with a similar thing in volume integral, because volume integrals can also be tricky, and I'm going to solve one problem. It's one of the problems in Griffiths. I believe it's 1.31, or yeah, it's 1.31, I believe. And this problem, let me pull out the statement actually. Volume integral, yes, this is problem 1.31. So we have third one, volume integral. And the statement of the problem is calculate the volume integral of a function t equals z square. So this is the function, it's given, t equals z squared, over the tetrahedron with corners at 0, 0, 0, 1, 0, 0. So we are going to make a tetrahedron with coordinates, corners at 0, 0, 0, 1, 0, 0, 0, 1, 0, and then finally 1, 1, 1. Now 0, 0, 1. And these coordinates related to x, y, and z values. Okay, let's make this tetrahedron. You know what a tetrahedron is? It's a shape you make by putting 4 equilateral triangles together such that their corners meet. So this is 0, 0, 0. Let's mark these. 1, 1, 1, this is x-axis, so let this be 1, 1, 1. Oh, sorry, 1, 0, 0. This is y-axis, let this be 0, 1, 0, and then this is z-axis, let this be 0, 0, 1. And if you join these corners, you see this shape is a tetrahedron. It's like 4 equilateral triangles, one lying at the base and 3 are standing but such that their heads meet. Okay, so you are supposed to calculate volume of this shape. Now the problem is, the main problem, like line integral, x, y, and z, they are all dependent on one and each other, which means that if you move small distance along x-axis, you are not only moving small distance towards x-axis, you are also moving some distance towards y or z-axis too. Yes, question.
Is the bottom an equilateral?
They are all equilateral. I mean, my drawing can be bad, but you can at least imagine it. Imagine 4 equilateral triangles. Equilateral triangles are triangles with all sides equal, side lengths equal. Okay, so one is lying at the bottom. This is, let's say, this one. Okay, and 2 are standing like this. 1/3 one is standing in front of us. So it's like a pyramid. Very bad pyramid, but still pyramid. You can just think about it, imagine it, and it will just be clear. Bad drawing. Okay, so you are going to find, in this case, you remember in the case of line integral, we had equation of line passing through 2 points in space. In this case, we are going to find equation of surface, because these are 4 surfaces which we have combined to make a volume shape, which is tetrahedron. Because each equilateral triangle, it's a surface. It's a 2-dimensional surface. And we have combined 4 of them to get some shape which has some volume, a 3-dimensional shape.
We need 4 of the ones you put on the board. I four sides that it makes with the axis?
No. So this is, let's say this one is in the bottom, and you erect two like this and one like this, such that their heads meet. So it's like a pyramid. Get it? Okay. So we are going to find equation of surface in this case. The general formula for equation of surface is, let's write it, ax plus by plus cz equals d. For now, you can just consider them as constants. In linear algebra, they generally represent the directions of four surfaces, but this is the general equation which you use to actually find the relationship. Once you do that, it becomes very easy. So you use these four coordinates term by term in this equation. For 0, 0, 0, it's trivial case. For 1, 0, 0, we have x equals 1, y and z equals 0. So this becomes x equals d, and this gives you the relationship a divided by d equals 1, right? When you use these coordinates, this gives you y equals d, and from here you get, in this case we have used the constant b, so this gives by b divided by d equals 1, because y is 1. And similarly, you do that for a third one, this, and this gives you z equals d, and from here you get c divided by d equals 1. You substitute these values of a by d, b by d, and c by d into this expression. You know, this expression can also be written as a by d x plus b by d y plus c by d z equals 1. And a by d, b by d, and c by d, they have the values 1. So if we substitute 1 for each of them, this is x plus y plus z equals 1. This gives us a relationship, this equation between x, y, and z. Like you change one of them and it will affect the other two. Okay. Now here at this point you have freedom, like which integral, since it's a volume integral, so volume integral will be it's like integral v, this function t d tau. Griffith uses d tau, so let's go with d tau, and this becomes integral volume t, which is z square, and d tau is dx, dy, and dz. If we first take x equals 0, then we have a relationship between y and z, and y will be 1 minus z, and x will be 1 minus z minus y. So these are the two limits which you are going to use in this integral. So let's come back to this integral, and this gives us z square dx, dy, dz. This is equal to dx integral, dy integral, and then dz integral, which is z square dz. Okay. Let's solve the x integral. Okay. So if we solve the x integral keeping the y and z integral same, so x integral goes from 0 to 1 minus y minus z dx. This gives us just x, 0 to 1 minus y minus z, and this gives us 1 minus y minus z. So now let's put this one into the remaining integral. So we have 1 minus y minus z, and then we have dy and z square dz. Okay, and y was 0 to 1 minus z. Where is y? 0 to 1 minus z. Now you solve the y integral, and if you solve the y integral keeping z integral intact, actually z integral, this should be here. And then we have for the y integral, this will give us just y, which will give us, okay, let me write it, y minus y square by 2 minus z will be constant and y, and this entire have integration 0 to 1 minus z, and then bracket z square dz. And now we have this will give us, this term will give us 1 minus z. This term will give us minus 1 by 2. So this will becomes minus 1 by 2, then 1 by 3. This will become y cube, and this will become 1 minus z cube. And then this third term will give us z is constant and integral of z is constant and integral of dy is just y, and this will gives us 1 minus z. And then you have a function of z square dz. Now you see we have everything in terms of z. So this is just like a sum of couple of terms, you can solve it, but let me recap it. So we had this configuration, and the problem with this was x and y and z, they were all dependent upon each other, just like the line integral, which means you needed to know how they depend upon each other, which means that you needed to know equation of plane, this general form of the equation. So in order to find this is the general formula, and then you substitute the values of these 3 points in this formula and find a relationship of a by d, b by d, and c by d. You use that values in this general equation and you find this relation x, y, and z. In this relationship you find limits. Okay, how do you find limits? You say that, okay, let me start my integration in the xy plane, in the yz plane. For this problem, that's your choice how you do it. So you substitute x equals 0 and you find the relationship between y and z, and so you find y equals 1 minus z. Then you go back and then you are like, okay, now my x limit will be 1 minus z minus y. And then since your x depends on z and y, it tells you, it gives you the hint that you do the x integral first. And once you do the x integral, you find your answer in terms of y and z. Then you do the y integral. You do the y integral and you find everything in terms of z, and then you do the z integral. Here you are supposed to do the z integral. So these are just bunch of terms. So this is like integral 1 minus z. This becomes minus 1 divided by 6 1 minus z cube minus z into 1 minus z. And then we had z square dz. Okay, so you can solve it. Its answer turns out to be, I believe, 1 by 60. Yes, the answer turns out to be 1 by 60. Okay, so you can just carry out this integral. We know the limits of z, it's from 0 to 1.